about it and we'll go over it.
Got one wrong.
Which one?
26.
26. Okay.
Hang on, Lauren.
Let's go.
All right, let's look at 26 here. So we have the square root of 10 times the square root of 15. So how do we do something with that?
You could make it 150 under its own radical.
5
Oh,
times 2 times 5 times 2.
We'll get that. We'll do that way in a minute, Henry.
And
We're
then,
gonna do it that way too.
25 is the only perfect square that can go into
25 goes into it
six.
times 6, so 6 times.
Then you have to like do your little thingy where you get the square root of that. It's 5 and 6 is in the radical.
6 is in the radical. Good. So Ben just said that we multiply them together. 25 goes into 150 6 times. Pull the 25 out, you get 5 on the square root of 6. Now Henry said that we can do it this way. 10 and 15. And you can figure out that 10 is 5 times 2. And the square root of 15 is 5 times 3.
Break both of them down and multiply 2 and 3.
Now hold on. What's the square root of 5 times the square root of 5? 5. So you can take that out. And then the square root of 2 times the square root of 3 is the square root of 6. Does that work?
Yeah.
Yeah. If you see it that way, can you do it that way?
Of course.
Yes, you can. Because what's our number one rule?
That's
If you don't like it, change it, right? Change it to what you do like. Okay? Now, is there another one that y'all want to look at?
No, then we're relatively easy. In the
Any of the 19 through 26? Any of them? Okay. Last chance. Okay. So now turn in your books to M3-7. Going backwards again. Going backwards again. Because we had to get out of order. No. We aren't actually. Okay. Let's look at number 1. It asks us to generate the first 4 terms of each geometric sequence. Do we remember what a geometric sequence is? It multiplies, right? It's a sequence that you multiply by the same number to get the next number. You can. It's multiplying by a fraction, right? That would be dividing. Same thing. Now, what do we know about geometric sequences? It multiplies, right? So let's find the first term of this geometric sequence. What would our first term be? If we wanted to find the first term, what number would we plug in for x? 1. So let's plug in 1 for x. 3 to the 1 minus 1 is what? What's 3 to the 0? 1. So 2 times 1? 2. Okay. Then we have 3 to the 2 minus 1, which is 3 to the 1, which is 3. What's 3 times 2? 6. Okay. Then 3 to the 3 minus 1. What's 3 to the 3 minus 1? 9. And then 9 times 2? 18. Now we've got 3 terms. Let's find our fourth. 3 to the 4 minus 1. Which would be what? 27 times 2? 54. Did we find 4 terms? Is this a geometric sequence? What's it multiply by each time? 3. 2 times 3 is 6. 6 times 3 is 18. 18 times 3 is 54.
That's pretty simple.
It is. Let's skip 2 and 3 because I don't want to deal with those. And then let's look at 4 here. Let's find the first term. You tell me.
It's 1.
1. Why is it 1?
Because 1 minus 1 equals 0, and then 0 to the fourth, or 4 to the 0th power is
1. And then times
-2
So-
would be a -2.
-2. Okay. What's our second term?
4 to the 1, or 4 to the 1th power, first power. So it's just 4 times -2 is -8.
-8.
I'm gonna guess it's -16.
Why do you say -16?
Because it's gonna be 4 times, never mind, it's gonna be double that.
It'll be -32.
-32. And then what?
Times that by 4.
-128.
-128. Oop. -128.
I'm definitely working on it now. I'm gonna get somewhere on it.
Is it easy to do it in your head?
No, yeah, and
Kinda, sorta, somewhat. Can we use a tool to help us out here? Yes, we can. Calculators. Okay, so turn the page.
back to 43.
No, just the 8. You see these graphs here? You have 1, 2, 3, 4, 5, 6 graphs, right? So on these 6 graphs, we're gonna have to figure out some similarities and some differences. So tell me some similarities you see between graphs. Are they increasing, decreasing? Pick and choose. Which ones are increasing?
Graph B, graph D.
Increasing, B and D, right? What about E and F? F is going up. Is it increasing?
No, because it's really out of order.
It's really out of order, right? Okay. So what about decreasing?
A and C.
A and C? Are they decreasing? A is C decreasing? It is. So A and C are decreasing. Now, what did we just say about E and F? What's going on with them?
Increasing and decreasing.
They're kind of back and forth, right? Kind of alternating. So alternate is E and F. They're kind of alternating back and forth, right? Okay. So what about the shapes of the graphs? What's the shape of all the first 4? What kind of shape is that? It's kind of like a little, what? Little curve, right?
Quadratic.
Not quite a quadratic. It's a curve, right? So they're smooth curves. Or what did you say, Matt? Exponential. They are smooth curves. And that is A, B, C, and D are all smooth curves. Because it's a smooth curve on all of them. Now, E and F, they're not curved at all. They're just kind of random. So no, not curved. E and F. Okay. So keep that name of exponential in your mind. Okay.
Yeah, we're gonna have to solve the problem and then put them on a graph.
Oh, you're just a page ahead of us.
No one's happy.
Is it that predictable? Okay. So now this time it just wants us to identify the constant ratio in each representation. What's a constant ratio? What's it being multiplied by each time, right? So if we look at our table, it goes from -2 to -6. What would the change be there? 3. What about -6 to -18? 3. So times 3 times 3. So we just said our common ratio is 3. Okay. Let's look at B.
Times 2,
Times 2. How did you get that?
because 45 plus 45. 45 times 2 is 90. 90 times 2 is 180.
Good. So it's multiplying by 2. So that means our common ratio is 2. All right. What about C down here?
Dividing by 10.
Dividing by 10.
Or 100.
Multiplying by what? 1/10, which is 0.1, right? You notice a pattern in these yet?
They multiply.
You notice a pattern in anything we're given?
On the right side of each equation is the ratio.
Is it just on the right side, or is it just because it's doing something specific?
It's doing something specific, but that's the only way I can really say it.
What's
know.
being done to each one of these?
They have exponents. I
They
guess.
have exponents, right? And it has a variable in the exponent,
That's why
right?
they're called exponents.
That's why they're called exponential, because they have a variable in their exponents. Light bulb moment.
No.
Yeah. Okay. So what about D? What's our common ratio?
1/2.
1/2. You can just look at it and figure it out, right? Now, is that true in our table?
Yes.
What's 0.5 times 1/2?
2.5.
2.5. What about 2.5 times 1/2?
1 and 2. 1 and 2.5.
1.25. So is it true?
Yeah.
Yes, it is. All right. The next one is what? -1/4. Yes, it is. What's -16 times a -1/4? +4, right? What about 4 times a -1/4? -1. So common ratio is -1/4. All right. And last but not least, F here. What's our common ratio? -3. Oh, times by -3. And that times by -3. So our common ratio is -3. Good. All right. So now it says, what strategies did you use to identify the constant ratio for each sequence?
Looking at the equation and checking.
Is that how we started it off?
No, we.
What did we do with the first few?
You just looked at it and do
Looked at the what?
the numbers.
The Y.
What is this called? Well, what is this called?
The
A
table.
table. We looked at the table. Looked at the table. And like Ben said, we determined what the Y value is changing by. And then Y value change. Okay. Oops, sorry, couldn't see that. Then we started for the last three. What did we do? We just looked at what?
Looked at it.
Looked at what? Looked at the equation. What about the equation give away the common ratio?
The thing with the exponent on it, the number with. the
Number with an exponent. Right? Are we done? We are.
exponent. For today.
No, not for today.
Right, 43.
No. M312. Analyze the graphs of the geometric sequences. Do any of the graphs appear to belong to a specific function family? If so, identify the function family. So that just asks, what kind of function are these? We said it earlier. Exponential. So these are exponential functions. Which ones are different? If we flip back, which graphs don't match up? E and F. Are E and F exponential functions? No, they are not. So exponential functions except E and F. E and F are geometric sequences, but not exponential functions. Why are they not exponential functions? What's different about their constant ratios? What? They're negative. The constant ratios are negative. And why does that matter?
Because it'll like make it a negative, positive, negative, so it'd be like.
Negative, positive, like flip and flop, right?
Like, yeah.
So it'll never just be a straight curve, right?
a straight
Good.
curve.
A smooth curve.
There you go.
There we go. All right, so now we look at this. A famous legend tells the story of the inventor of the game of chess. When the inventor showed the new game to the Emperor of India, the Emperor was so astonished, he said to the inventor, "Name your reward." The wise inventor asked the Emperor for 1 grain of rice for the first square of the chessboard, 2 grains for the second square, 4 grains for the third square, 8 grains for the fourth square, and so on and so forth. So number 1 asks us to determine the number of rice grains on the next 4 squares and include them in the table. So
16, 32,
16, 32, 64, and 128. Now, how did you get those values?
It's going by 2 every time.
Going up by 2 every time. Multiplies by 2, multiplies by 2, and it just keeps going, right? Okay, now it wants us to write it as a power. So to write it as a power, we noticed that in these, our common ratio was raised to the exponent, right? Right? So now, what's our common ratio?
Number of rice grains.
Which is, what's it changing by our common ratio? 2. So 2 to what power is 1? 0. 2 to what power is 2? 1. 2 to what power is 4? 2 to the second power, which is 2 squared. What about the next one? 2 to the third power, which is 2 cubed. And then 2 to the fourth, and 2 to the fifth, and 2 to the sixth, 2 to the seventh. Does that make sense of why it grows like that? Because we got 2, then 4, then 8, then 16, 32. Right? Okay. So what pattern do we notice in the table? What's going on here?
The power increases by 1.
Power increases by 1, but look at the number of rice grains. What's happening to it each time? It doubles, right? So it doubles. It doubles. Okay, so let's look at 3. And it says graph the points from your table. The first few points have been plotted. Describe the meaning of the plotted points and then identify the function family represented. So what was our value? It gives us for 1, 2, and 3. It is exponential, but we got to plot our points first. So what was our value for 4? What? It was 8. So we plot it right here at 8. What was 5? 16. And then 6. 32. 7. 64. 8. 128. Did we have a value for 9? Oh, but what would it have been?
Something opposite that.
256 would have been way off our graph. It would have been way up here somewhere. Okay. So then it says describe the meaning of the plotted points and identify the function family represented. What kind of function is this? Exponential function. Just going to keep writing this over and over and over again. Exponential function. I could spell today. All right, now identify the constant ratio in the graph, in the table, and in the situation. What do we say our constant ratio was? 2. All right. Turn the page. Now we're on M314. And we're given this right here. F of x equals a times b to the x. And that is how an exponential function is represented. So then it asks us, what does the a value and the b value represent in this exponential function? So let's look at this. A is here, b is raised to the power, right? So what did we call the number that was raised to the power?
The ratio.
The common ratio, right? Constant ratio, common ratio, whichever way you want to call it, but constant ratio. What would A represent? Let's go back and look. If we wanted to find the 0 for X value, right? Let's look at that. This is increasing by 2 each time, and we want to go backwards to find the value when X is 0, right? So how would we go backwards? Instead of multiplying by 2, we would divide by 2. Okay, so what's 1 divided by 2? Oops, sorry, you can't see that. Sorry, what's 1 divided by 2? 1/2. Still can't barely see it. There it is. So all we did was figure out the value for 0 here. It's 1/2. So let's think about this. If we wanted to create a function for this that we were given here, right? How would we create a function for this? F of x equals a times b to the x, right? Now we said the constant ratio is b, right? So our constant ratio was 2 equals f of x. Now if I wanted to plug 0 in for x, what's 2 to the 0 power? 1. How can I get 1 to be 1/2? Divide it by 2 or multiply it by 1/2, right? Multiplying by 1/2 is the same as dividing by 2, right? So then, does that function work? 1/2 times 2 to the x. We made it for 0, right? Well, what about 1? 2 to the 1 is what? What's 2 to the first power? 2 times 1/2? 1. Then 2 to the second power? 4 times 1/2? 2. Is that our value for 2? Can we keep going? Yes, we can. So did we just find a function for this? Yes, we did. Now, if you notice, the 1/2 is when x is 0. What do we call when x is 0? Y-intercept. So our a value represents our y-intercept. And now we have our A is our y-intercept and our B is our constant ratio. So now it asks us to use the exponential function and a calculator to determine the number of rice grains that would be on the very last square of the chessboard. A chessboard has 64 squares. Now we know the equation is f of x equals 1/2 times 2 to the x. How can we find how many grains of rice are on
2
the
to the
64?
63rd power divided by 2.
2 to the 63rd?
Yep.
We would go the 2 to the 64th. We would just plug in 64 for x. So we have f of 64, because we want to find the 64th square. And we have 1/2 times 2 to the 64th power.
Yeah, put that into your calculator.
I will. So we have 1/2 times 2 to the 64th power. What does this e to the 18 mean?
It means that number to the 18th power.
Close. Let's write it out. 9.22. And then what do y'all remember what scientific notation is? Times 10 to the 18th power. What does it mean if I raise 10 to the 18th power? 18 zeros. So really what we're going to do is we're going to move this decimal how many times?
A lot.
18 times. So if I had moved that decimal 18 times, how big is that number going to be? Pretty big. Is there that many rice grains in the entire world? Probably somewhere, probably not though. That's a lot. That's way, way, way too many. Yes. So if you think about it, this guy really set himself up for life, didn't he? He's getting all the rice he ever wants. But if you're the king and this guy just tricked you into giving him all the rice that you have plus more that you can't afford, what are you going to do to that guy?
Kill him.
You're going to kill him. Right?
Yeah.
That's how they used to do it, right? They used to off with his head, right? So did he use this math very, very wisely? Yes. But if we go too far, what happens?
Math could get us killed.
It won't get us killed, but it can hurt us, right?
It might.
It might. Probably not. Not in today's time, but
Okay.
be careful what you do your math with. So now, turn the page. And turn the page again. So now you have 4 problems right here. 4. I'm going to do the first one with you. And then you do the rest. That's all you're going to have to do today. No. No. Okay. So is it? We'll see. Okay. So we're looking at this and it asks us to find an exponential function in the form f of x equals a times b to the x. That just asks us to write an exponential function, right?
Yeah.
So how do we find what our a and b are?
A is 4 because we have x's still y, so A has to be 4.
A is 4 because our y-intercept is 4 times, what's our common ratio?
Looks like it's dividing by 2, so multiplying by 1/2.
Dividing by 2, which is multiplying by 1/2. All right.
4 times 1/2 to x.
So we have 4 times 1/2 to the x. And then what are we missing? Is this an equation?
The x.
Not the x, but the f of x. And f of x is another way of saying y. So, are we done?
Well,
Did
did
we-
you
yes.
say equation? Yes, we're done.
Did we find it?
Yes.
We're done. So now you have 3 problems to do on your own. And then we're done. That's all you gotta do today. Easy, easy assignment. Work it out.
Go for it.